Okay, class. So let's continue with the deformation of solid. We finished the topic today. Okay, I think 10 of you here. I think we can start. Okay, so hope everyone can see the slide. You can see the slide, right? Can okay. So just recap what we learned about deformation of solid. What did you learn so far? First thing you learn about Hooke's law. What Hooke's law said? Extension proportional to the force applied, as long as never exceeds a limit of proportionality. After Hooke's law, what do you learn? Spring in parallel and series. How the extension is going to react. Parallel, the extension is going to be lower. Series, the extension is going to be higher. Okay. Then series parallel discussion. We introduced with a new term called stress, strain, Young modulus. Okay. What is stress? Force acting normally per unit area. Okay. Unit Pascal. What is strain? Is the ratio of extension to the original length. Uniless. Then what is Young modulus? Is the ratio of stress to strain. Okay. Unit Pascal. What Young modulus measures? Stiffness of a material. Then we talk about difference between Young modulus and spring constant. What is the main difference? Spring constant dependent to the dimension of the material. Young modulus is independent on dimension of the material. Okay, material at any sizes. If aluminium is a smaller plate or a thicker plate, the Young modulus will be the same. Okay, but spring constant, a thicker wire or thinner wire made of spring, the spring constant will change. Okay, then we talk about the experiment about how to find the Young modulus. Use a longer wire, thinner wire, reference wire, vernier scale to measure to reduce the percentage uncertainty in the Young modulus. Okay, so in this graph here, can you identify all the points here? A, B, C, U, and F. What is A? A is limit of proportionality. B is elastic limit. Elastic limit is the end of plastic deformation. C is yield point. Okay, C we call it as what? Yield point. Okay, class, you can listen my voice, right? No problem. Okay. Sorry. So C is a yield point, very low profile, the beginning of plastic deformation. U is what? Maximum tensile stress, the maximum stress ever experienced by the object before break. F is breaking point. Okay, so this all we done. Ductile material will experience necking. Necking means we know it's going to certain position get weaker, so you're going to break at that point. Necking happens. Necking happens at the ultimate tensile cell normally. Slightly earlier, you can start see the necking. Okay, what is ductile material? Type of material obey experience elastic and plastic deformation. It's a ductile material. Okay, this is glass. Glass is brittle. Brittle stress to strain is going to be most likely is going to be a straight line. Only at the tip, a slight curvature happens. Brittle, a material that does not undergo significant plastic deformation. Okay, does not undergo significant plastic deformation. No necking. This all we done. Okay, now third one today, rubber. This is the last category of the material, rubber. Stress to strain, a rubber going to make a curve like this. It can have a strain of 8. This is the indication that it's a rubber. The strain will be very huge, about 8. Then you can categorize this as a rubber. And rubber obeys Hooke's law for only a small part of its extension. Yeah. The Hooke's law is only obeyed at a small part of the extension. But the entire region is the plastic deformation, elastic deformation, no plastic deformation. Okay. Break after large extension has been produced. So that is rubber. Rubber special character is what? As a strain of 8, only exhibit elastic deformation. No such thing as plastic deformation. Okay, and it's as a last extension. Large strain means last extension. Okay, so these are the 3 different graphs scientists found. Stress to trend, copper, one of the representing the ductile material, glass representing brittle material, and rubber. Rubber is rubber. So it will have a huge extension and a huge strain. In exam, they will show this graph. They will ask for the which type of material. But nowadays, I think the ductile, brittle, polymer also has been removed from your syllabus. They should not ask about that. They now more asking about what is the area and the graph represents, what is the gradient represents, and so on. That's what main focus now. Okay. Okay, compare the gradient for each material, comment the extension of each material for the same load. Yes. So copper, glass, rubber, which has the greatest Young modulus? Compare the gradient. So copper has the greatest Young modulus because of what? Gradient is the highest, followed by brittle, and the rubber has the lowest Young modulus. Less stiff. Comment on the extension of each material for the same load. Of course, the highest extension is yielded by the rubber, and followed by glass and copper. Copper has the greatest Young modulus. Okay. So brittle means when dropped, it shatters. That's brittle. Like if it's a ductile, when it drop down, like a ductile, it changes shape. Okay, the shape changes. So it exhibits plastic deformation. Ductile. On the left can say it's ductile. On the right should be brittle. Okay, we already talked about strain energy. The energy stored in the deformed material is called strain energy. The area under graph of force versus extension is strain energy. It is also known as elastic potential energy. Got lots of names. Strain energy, elastic potential energy also sometimes we can call. It will exist elastically. Strain energy, elastic potential energy is like the 2 terms we apply. Area under graph. So force versus extension, area under graph is strain energy. Okay, strain energy. We know it's half fx. As long as never exceeds limit of proportionality, we can use half fx. So, okay, force versus extension, area under graph is energy. Okay, because Newton per meter is joule, so energy. Stress versus strain, the area under graph, what it represents? Anyone? The stress to strain, the area under graph represents what? What is the unit you get? Stress to strain. Pascal divided by uniless, you get Pascal also. But they said area below graph also is strain energy per unit volume. Okay, strain energy per unit volume. You see, how could be strain energy per unit volume? You see, strain energy. Strain is what? Unit joule. Per unit volume is what? Per meter cube. Okay. You expand this joule, you expand the joule in terms of base unit, you'll get what? Or put it in Newton, it will be Newton per meter. It will be Newton meter, sorry. Joule will be Newton meter. It's meter -3. So at the end, you get what? Newton per meter square. If you still remember, Newton per meter square is actually what? It's Pascal. It's Pascal. The area in the graph is actually Pascal, right? Because the y-axis unit multiplied by the x-axis unit should be the unit of the area. So it's Pascal. Okay, but Pascal, very rarely, Pascal also can be written as joule per meter cube. Okay, joule per meter cube. So what is meant by joule per meter cube? Energy stored per unit volume. Okay, that's why I say area below graph is actually also strain energy per unit volume of the material. Let's say you have a material, when you apply a force, so you're going to extend, how much of strain energy stored per unit volume of the material. Okay, per unit volume of the material is the stress versus strain area under graph quantity. So both the energy, force to extension energy joule F of Fx, we know this quite well. Stress versus strain, now something new, strain energy per unit volume. Okay, joule per meter cube, or you can put it Pascal. Okay, so both the energy. Any questions from here? Okay, so something new, strain energy per unit volume. Okay, so now your turn. Let's do one by one. A wire of cross-sectional area 0.65 millimeter square and the original length is 80 centimeter is stretched at both ends by a force of 30 Newton. Calculate the stress on the wire. Okay, so warm up. What is stress? Stress is force over area. Okay, force over area. So what is the force you apply? 30 Newton. And what is the cross-sectional area? 0.65. Change to meter. Millimeter square change to meter is 10 to the power of -6 meter. Then you should get this answer. 4.62 times 10 to the power of 7. Okay. 10 to the power of 7. Yeah, 6. Yeah, 46. So 10 to the power of 7. Okay. Okay, next. If the extension is 0.12 centimeter, what is the string? So what is strain? So strain is extension over the original length. So extension 0.12. Length is how much? Length is 80 centimeter. So you get the strain. You get the strain. So you should get 1.5 times 10 to the power of -3. No unit. Okay. The next, calculate the Young modulus. Of course, stress over strain gives you Young modulus. The first answer, Young modulus is what? Young modulus is stress to strain. So the first one divided by the second one, you get the answer for the Young modulus. So you should get 3.08 times 10 to the power of 10. Okay, this warm up, not that difficult one. What is the strain energy in stretched wire? How much of energy stored in the stretched wire? So strain energy, what is the formula used? Strain energy, the energy also symbol is EU, so R Fx is the strain energy. But with one condition, what is the condition to use this formula? Anyone? What is the condition to use this formula? We are assuming that it never exceeds limit of proportionality or elastic limit. Never exceeds what? Anyone? Half Fx is only can be used with one condition. The material never exceeds limit of proportionality or elastic limit.
Limit of proportionality.
Yes, good. Limit of proportionality. And don't ever say elastic limit. So should be half times F is what? F is 30 Newton. So direct substitution 30 times X. X is what? How much is X? 0.12. But 0.12, make sure unit conversion times 10 power of -2. So you get the answer in joule. Okay. So half times 30 times 0.12, the extension. So you should get 1.8 times 10 to the power of -2. So stress, strain, Young modulus, and strain energy. Quite a straightforward question. Okay, so let me go a little more deeper. Any questions from here? No questions, Okay. So now we're going to talk about something called energy lost. Okay, force versus extension. When you apply a force, this area is work done by you. Work done to stretching the wire. This is the amount of work you done by you to stretch the wire. Okay. So let's say you pass the you pass the elastic limit. You already passed the elastic limit. Let's say it's under plastic deformation. When you let it go, the wire will go alternative path. It takes alternative path until it reach a permanent deformation. This is permanent deformation. It's permanently deformed. That means already spoiled, permanently deformed. Okay. The area under graph in the second region is the energy recovered. The energy you get back. Okay, like let's say you have a string. Okay, so you archer, so you launch something. The let's say the what do you call, the rubber was extended up to plastic deformation. Let's say it extended up to plastic deformation. Okay, when you stretch it, let's say you did 10 joule. You did 10 joule. The entire area is 10 joule. When you let it go, because it's already in the plastic deformation region, the energy you recovered will be smaller than the amount of work you done, 10 joule. But energy recovered, maybe this area, maybe it's 8 joule. Okay. So how do you know energy recovered? The energy is recovered will be in form of the kinetic energy of the object you are launching. So if you reach a plastic deformation, energy you stored greater than the energy recovered. Okay. In exam, they'll ask you to shade the region which is energy recovered. Okay. So area under graph of the second line is energy recovered. Okay. So the border, the area which bordering the two lines is called energy. I won't say lost. Please remove the word lost, because it has a permanent deformation. It has a permanent deformation. So we say energy is trapped. Okay, it's trapped. Energy is trapped in the material. Why is it trapped? Because there is a permanent deformation. So therefore, we say energy is, won't say lost, we say it's trapped. Please change, just like. So this is energy trap. Okay, energy trap. Okay. So force versus extension, you should know which is energy stored, which is energy recovered, which is energy trapped. Okay. Sometimes they will try to confuse you. Instead of force versus extension graph, they might plot extension versus force. If it's an extension versus force, okay, so let's say you extend it until plastic deformation, the graph will go like this. Okay, where's the energy stored? This is your energy stored. This will be your energy stored. Okay, your y-axis is the energy now. Okay, and of course, when you let it go, you take alternative path, come back here. So which is the energy recovered? So this is your energy recovered. Okay, this is your recovered. Okay, recovered. Okay, this is the energy recovered. Okay. Okay, so now which is the energy lost? So the area between these two regions, this is the energy lost. Sorry, not lost, trapped. The energy trap. This will be the energy trap. Okay. Okay, so be careful. Whenever you do this question about energy check, is it force versus extension or not? Sometimes it will be extension versus force. Then the area will be bordering the y-axis. Any question from here?
Yes, I have a question.
Yeah.
How do you know how much is the permanent extension after it is over its limit?
How much is the permanent extension? That means you are saying how many centimeter will be permanently extended, is it?
Like when we draw the graph, how do we know like how much to?
Oh, okay.
Because like
are,
how the gradient will be.
in your real life, you cannot sketch. If they ask you to sketch, you can sketch. Sketch means the value we cannot determine it. It's only sketch one. But if you want to get actual graph, you have to conduct the experiment. You load it, then you do unload it. When you do unload it, you get every coordinates. Then finally you can see what is the permanent deformation. Okay, so if you conduct experiment, you get the data already. You load it, the line will go up. When you do unload it, the line will go down. So you can see finally where's the permanent deformation when you conduct experiment. If in exam you didn't conduct experiment, they only ask you to sketch, then you can have any permanent deformation. Like have a small permanent deformation to show that there will be a permanent deformation. That's it. How much you can't identify because you didn't conduct the experiment. Understand? Okay. 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 So let's proceed. Rubber. You see, rubber acts quite differently. What different? You see, when extend, okay, when it extend, it takes this path and it extend. So what is the energy stored? When you extend, so of course, this is the energy stored. The entire thing will be the energy stored, okay, in the material. Okay, when you let it go, the rubber will go back alternative path. It will take alternative path, but the only feature is go back to the original length. Go back to the original length. So this means the shaded area is trapped or lost. Shaded area is a lost energy. This is confirmed lost. Energy is lost. For a rubber, energy is lost because there is no deformation, no permanent deformation. It already get back to original length. That means all the energy should be released. So some energy is lost. This is lost for rubber. Rubber energy is lost. For ductile, brittle, energy will be trapped. Okay. So this is lost. So this is called hysteresis loop. Very low profile term. They won't use this term. But you should know that the two border, the area is the energy lost. Okay, so we are almost to the end of the topic. Okay, so this is about energy. Okay, so energy, stress, force versus extension is energy. Stress and strain is energy per unit volume. Okay. Okay, 1 minute for you again. Try, give me the answer for this. 1 minute, work out. Take your calculator. Try to figure out the answer. Okay, so the aluminum rod is original length given. Cross-sectional area is given. Compressed in a Y so that the length is reduced. Oh, now this is compression. Compression or extension. X is going to be the X. The X can be compression, can be extension in the formula. The Young modulus formula is what? Force, area, extension, original length. This could be extension or could be compression. Okay, works the same way. So the length is reduced to 0.01%. How they give percent? This 0.01% is what? X over original length times 100%. Okay, so X over original length times 100% is 0.01%. Okay, so for me, I think you can find the X over L already together. So X over L, how much? X over L will be this 0.01 divided by 100, X over L. Then we can place here, X over L. We bring the L down, it's X over L at the bottom. Okay. This can be written as F A L. You can bring down, you can put it like this, X over L. Mathematically, this and this is same. The L, when you bring down, you can put X over L. Okay. So X over L, you can replace with 0.01 divided by 100 into here. Then you can work out your whatever elastic energy. They want elastic energy, sorry. how much elastic energy is stored in the material. But before that, what force must be applied? So they're asking for F. So can you find the F? So Young modulus is F over A, the extension over the original length. You put it down. Okay. So you know the extension over the original length, 0.01 divided by 100. Area, what is area? Area given 1.2 times 10 to the power negative 4, and Young modulus also 7 times 10 to the power 10. So you can find the force. So what is the force you get? So hope everyone getting the same answer. So you got 840 Newton. Anyone got a different answer? So all of you should get 840 Newton. Just substitution one. Okay. So I believe everyone managed to get the answer. Just the only problem is they give X over L together. The X over L times 100% is 0.01%. Okay, next, how much elastic energy is stored in the rod? How much elastic energy is stored? So what is the elastic energy formula? Of Fx. That's it. So recall back. Get me the answer. Okay, now you need to know the extension. So now you have to calculate the extension now. So extension of length times 100%, we know 0.01. Length we know is, do we know the length? The original length is 150 mm. You can find the extension from here. Okay, so I think you need to do some work to find the extension. Force, you know already. So it's going to be half times F is how much? F is, where's F? Force applied? Oh, force they didn't tell, compress. How much energy, force you calculated earlier one, 840 Newton. So force is 840 Newton. But extension, okay, anyone, what is the extension you got? So let me do on top. So what is extension? Extension over the original length is found to be, what? 0.01 divided by 100. I think you can find the extension. Just substitute the length. Length bring the other side. So length will be how much? Cancel the length here. So X will be, length is 150 millimeter, loss of conversion. So it's going to be 0.15 meter. Put it in meter. Then this, you place the extension, then you get answer. So what's the answer you got? Anyone? So I believe you get 6.3 times 10 power negative 3. Does anyone get a different answer? So all of you got the same answer. So yeah, let's get the extension from X over L. X over L is 0.01 over 100. Okay, still the question is not that challenging, still is fine, manageable. Only something different in this question is X over L together is given. Okay, so now it's going to be your past years. Okay, past years going to be asked differently. Okay, let me go quite fast. First question. What's the answer? What does the shaded area represent? The energy transformed into heat during the complete cycle. The recoverable elastic potential energy stored at a maximum extension. The work done on the sample while loading. The work done on the sample while unloading. Okay. So, anyone? What's the answer? Okay, what's up? Okay, you need to understand, when you do work on the sample, when you do work on the sample, the sample will gain potential energy. When you do work on the sample, when you extend it or when you let it go, like you bring it back to the original length. You do work on the sample when you extend it, okay, or when you compress it. Work is done on the sample, okay. So C and D cannot be the answer. The work done on the sample while loading. No. Work done on the sample while loading is the entire area of the above border. Okay, that is work done on the sample. See the work done on the sample while unloading. Okay, yeah, good. This area shaded region is the energy involving when you do unloading, but not work done on the sample. You didn't do work done on the sample because you are bringing it back to the original length. You didn't do any work on the sample. Why? You are just bringing back to the original length. When it's bringing back to the original length, the body is it gain potential energy. The material loses potential energy. If you do work on the sample, the body must gain potential energy. Then you did work on the sample. So T, although they talk about unloading, but they should say the work done by the sample. Instead of on, they put by. Then D could be correct. Okay, by the sample. The work done on the sample while unloading is not that area. This is work done by the sample. Okay. So how to know when you say it on the sample? If you do work on the sample means the sample must gain potential energy. Then you did work on the sample. When that happen, when you stretch it, it's work done on the sample. Okay. So D cannot be the answer. The best answer is, of course, it should be the B. The B. The recoverable elastic potential energy. The potential energy which is recovered at the maximum energy. So answer should be B. The energy recovered. Recoverable elastic potential energy. D is like mistake because they say on the sample. Should be by the sample. Then D could be the answer. Any questions from this question? Anyone? Don't have. Understand? Work done on the sample means the body must gain elastic potential energy. Then you did work done on the sample.
I have a question.
Yeah.
What does work done on the sample mean?
Work done on the sample means like you see, when you're going to use energy, when you stretch, you feel tired, or when you let it go, like you go back to the original length, you feel tired.
Oh.
When you feel tired, when you
After
stretch it, right? You know there is some exercise machine with a spring, chest expander. Okay, when you stretch it, you feel tired. You feel like, oh my god, need to do that. Or when you let it go, you feel tired. When you stretch it, right?
Stretch it, yeah.
When you stretch it, you did work on the sample. The sample gain potential energy. Okay. So when you let it go back to the original length, you didn't do any work. You feel like relax, what? You just let it go. You just move it back to the original length. You didn't do any work. When you stretch it, you did work on the sample. So what is the proof that you did work on something? If you did work on something, a material, the material must gain potential energy. Okay. So when stretching on the sample, when unstretching, you are not on the sample. It's by the sample.
Yeah.
Okay, the sample does work. Okay. Okay. So as we move on, more questions. Okay. This is a challenging one. 1 minute for you. Everyone, please send the answer to the WhatsApp. 1 minute. My advice, diameter change to area. Okay. Diameter, put it in area. And the diameter is D, area is A. When the diameter is 2D, area is 4A. When the diameter is half, a quarter A. Put it in area to be easier. Okay, so anyone? I haven't received any answer yet. A wire stretched 8 mm under a load of 60 Newton. Okay. So wire was stretched 8 mm under load. So there is a wire. It was applied a force 60 Newton. And it was stretched 8 mm. It means the extension is 8 mm. 8 mm, okay. Yeah, that's the story. Okay, now a second wire of the same material with half the diameter and the quarter the length of the first wire is stretched by the same load. Okay. Second wire has half the diameter. So half the diameter. That means the first wire diameter D, but I say I don't want to put D, I want to go for area. So I take it A. Area is A. Diameter D, area is A. Then the diameter become half. If diameter become half means how many A is this? This should be A over 4. The area. Sorry, A over 4. Should be A over 4. And the length is how much? Length is quarter length. That means this we take it as L. This was quarter L. It was a quarter L. And it was applied with the same force. 60 Newton. Okay, 60 Newton. Assuming laws of it, what is the extension? They're asking what is the extension of this wire. They're asking how much the X here. Okay, this is the what do you call the simplification of the question. A wire with A, L, 60 Newton, extension is 8. Another wire with quarter A, quarter L, same load, 60 Newton, what is the extension? Okay, how do you make equation? What equals to what to start the working? What equals to what to start the working? The road to find the X. Anyone?
Area of circle.
Yeah.
Yang
The both
modulus is equal.
the both body has what same? The both
Yang
wire has
modulus.
what quantity same?
Yang modulus.
Yes, Young modulus. The Young modulus of the first wire is the same as the Young modulus of the second wire. The Young modulus is same because it's made of same material. Same material means the Young modulus is same. Yeah. Can I put in all the information? You get the X ready. So Young modulus, what's the formula? F, original length, extension, area, and the extension, right? So put all your information. F is 60. L is how much? We put it as L. They never said how much the L, just put it L. Area for the first one is A. Extension is found to be 8 mm. Do you need to change 8 mm to meter? You don't need to change because it's a identical formula. Right? This also F L A X. Okay, in science, if two equations like identical, like Boyle's law last time, P1 B1 equals to P2 V2. If the formula is identical for the unit quantity, you can put any unit you like because the unit going to cancel. So here, don't waste your energy changing 8 mm to meter. You can leave it as 8 mm. So you can leave it at 8 mm, but finally you should know the extension also. You get the same unit as the unit you used here. Okay, so we leave it as 8 mm. We are looking for x area now. This area is A over 4. Okay, and force is 60, but the length is a quarter length, L over 4. Okay, this is how you input the value. So find the x. How much the x you got? After this is met. Okay, so I receive answer. So anyone? Yes, good. So I receive C. The answer is going to be the same extension. So both going to be C. You see, you rearrange and check the value for x. It will be 8 mm. It will be 8 mm. Okay. So this is how you need to do the working. My advice: diameter change to area. It make easier for you to calculate. If you put here diameter, it's going to be pi d over 2 squared. The numbers get more complex, more chances to make mistake. Diameter convert to area. Okay, so answer is C. Same material means both of them have the same Young modulus. Okay. Okay, so let's try to get the momentum for the next question. Okay. So we go to the next one. The next one is this. Okay, try to give a try. Okay, I'm going to erase everything. Can I erase everything? Okay. Okay. Next question. 1 minute for you. Please, most of you can give you a try and give me the answer. Only 3 or 4 of you just giving me the answer. So 12 of you in the class. So expecting many to join. You mean giving me the answer? Okay, this time I wait for your answer. Give me answer. Try to calculate. You can draw 2 wires. I like to draw 2 wires. Then I state everything into the diagram. I feel it's easier for me to visualize it. You can draw 2 wires. Okay, so I receive answer. Now if you say the answer is B, the ratio is 1. So is it 1? This answer is B. Okay, only one answer I received. The others? Two wires P and Q made from the same material. That means both of them have the same Young modulus. Wire P is initially twice the diameter, twice the length of Q. The same force. Each wire causes wire to extend elastically. What is the ratio of extension? So wire of P, wire of Q. Okay, I received another answer stating A, half. Is it half? Okay, let's see. One said B, one is said A. So let's withdraw. P is twice the diameter and twice the length of the Q. So Q we make it as like Q Q, we make it area A, and the length is L. P we change. P, the diameter is what? Twice. So P, how many A? P is how many A? It's 4A. The area is 4A. Okay. Another one said is A. Many of you saying A. 2 of you saying A. As you see. The length becomes 2 times. Length is twice. Okay. Length is 2L. And the force is same. Both apply with the same force. So now they're asking, what is this extension P, extension Q here? Asking what? What is the ratio of extension of P? So they're asking for extension of P over extension of Q is what? This is the question. So A for A, L to L, F, F. Okay. So as usual, so when you say A, okay, so you put the values. So the Young modulus of P must be same as Young modulus of Q. Okay, I'm receiving more answers with A. As you see. So Young modulus P is what? F times how many L? 2L over A is what? For A, extension is extension of P. Extension of P here. Here F, L, A, extension of Q. Okay. So looking for extension of P over extension of Q, what do you get? So you bring the other side. Yes, good. You got R. Okay. So good. Those who got A, very good. This should be R. Right? Should be R. What? The F is the same. This is 2L, this L. This 4A, A. So XP, XQ. You're looking for XP or XQ. So XP bring up. So after this is maths. So XP or XQ, you get R. So the extension ratio is R. Good. My advice again, the diameter is troublemaker. Change to A. DA means 2D is like 4A. 3D is like 9A. Half D means like quarter A. Square the ratio. Okay, so far so good. I think many of you getting me the correct answer. We go for the next one. Hope everyone get the same answer. So next one. Okay, next, another one. Okay, 24. This question is a little tricky, but be careful. Give me the answer. Hope everyone giving the same answer. Come on, what's up? Okay, so hope to receive answer. So I receive one answer, D. Is it D? 2E. Is it the Young modulus for the second material is 2 times of the first one? If this question is tricky, but if you really understand the question, the working is the shortest among the other two. Or I can say that apparently no working. Yeah, I receive another answer, C. Yeah, receiving more answer, C. 2 of you say C. One you say D. C or D?
C.
So it should be C, right?
Yeah.
Same Young modulus, right? Why you say it? What statement above you should conclude it's the same Young modulus? Okay, how do you know it's the same Young modulus? Both of them made of the same material. Both of them are steel. Right? Both of them are steel, what? So if they made of same material, the Young modulus have to be the same one. Dimension never affects Young modulus. So this question is a little tricky. No working. Because they said both are made of same steel. So the Young modulus have to be same, E. So 24, the answer is E. Reason is what? Both made of same material. Therefore, you increase the length, increase the cross-sectional area, won't change the Young modulus. The Young modulus is E. Any questions? No questions, eh? So everyone agrees E, eh? Because same material, both are Young steel. Okay. Okay. The what do you call the length twice the half the diameter, they just want to try to trick you. Okay. So you have to be very concrete with your idea. It's E. Okay, let's move on to the another one. This one. Give me the answer. Don't give up. Do more questions. You will get a better understanding. The energy stored in the rubber for extension 5 meter. What is the answer for this? The energy stored in the rubber for an extension of 5 meter is, so area under graph, right? So area under graph. I'm receiving answers. So yeah, I think A, right? All of you said A, 2 of you said A. It should be A, right? Because the triangle, if you make a triangle like a triangle, it's a triangle. We know the area is half times, but 5 times 40, right? So it's 100. So this curve down, so it's less than the triangle, so it should be less than 100 joule. So of course A is the answer, not a challenging one. Okay, so answer is A. Okay, another one. 16. What's the answer for this? The bungee jump. Maybe some of you have tried this before. Okay, what type of energy change happens? Me answer. At the beginning, it has potential energy, of course, gravitational potential energy. When you go down, gravitational potential energy is converting to what type of energy? Gravitational potential energy is changing to kinetic energy. Okay, so many two of you give me and the answer C. Is it C? What are the kinetic and elastic potential at position 3? Position 3, it already stopped, right? Position 3 is already stopped. So it's already stopped. So EK have to be, EK, if it stops, that's right, until the lowest point of the jump. So lowest point of the jump, EK have to be 0. E, gravity, GPE, and the potential, GPE, the gravitational potential energy should be the minimum. Okay, it should be the minimum. All change to what energy? all change to elastic potential energy. Elastic potential energy should be maximum. Okay. So many say C. Many of you say C. Yeah, C. So everyone agree. Good. Everyone go to the same common answer. Elastic potential energy is maximum. Kinetic energy is minimum. Or another word, kinetic energy is zero. So answer should be C. So at the beginning, what type of energy possess? GPE. It's I GPE. While going down, what happened? The GPE is converting to EK plus elastic. Elastic. But when go towards the end, okay, GPE and kinetic both will convert to elastic finally. So finally become all elastic. Okay. Okay. Do we done this question before? Yeah, I think you done this. Done this in your early. We skip this. Okay, 23. Come on. Now the thing going to move faster. 23. Give me the answer for this question within 2 minutes. Real examination, 40 questions, 1 hour, 15 minutes. So one objective you must do within 2 minutes, less than 2 minutes. 23. This style of question is very common in past year. The length is double, area is become half. What is the new extension? Very common. So better adapt to this style of question. Okay, so I receive answers B. So what have you said B for mm? The others, give a try. Receive one answer. Oh, okay, 2 of you said B. Is it B? The others? 4 mm. So draw the two wires diagram, then you can able to find. Wire stretched by 8 mm and the load is 60 Newton. So wire stretched by how much? Wire stretched by the extension was found to be 8 mm. 8 mm. When applied by what? When applied by. Okay, can't see the. Okay, when applied by 60 Newton. Okay. Okay, class. So I think all of you giving B. So I believe it should be B. So this is L. The area we take it as A for the first one. The second one, what? The extension of the wire, same material, having 4 times the cross-sectional area. So A become 4A. Okay. And the length is what? The length is 2L. L become 2L. It's 2L. Sorry, it's 2L. So they're asking what is the new extension. And force is still 60 Newton. So what is the extension? So of course, the Young modulus. So what? 60 times the L over the area is what? A. The extension is 8 mm. No need to change the unit. Is equals to 60 times how much? 2L over 4A. New X. So yeah, it makes 4 mm. It makes 4 mm.
Sir, I have a question. If they stated same material, is it have the same Young modulus?
If they didn't state same material. If they state same material, then the Young modulus is same. If they never state same material, then you can't take it as Young modulus same.
But the question stated that extension of a wire of the same material.
If same material, Young modulus have to be same.
Oh, okay.
Same material means Young modulus is same. Okay, because Young modulus like a density, never change for a material. Dimension different, different thickness, different length. The Young modulus is same for the material. Okay. Okay, 24.
Teacher,
Next question.
teacher,
Any question?
I have a question on the 23.
Yeah.
When do I need to square the diameter, the ratio for the diameter?
When they give diameter, when you convert to area. When diameter convert to area, you square it.
Okay. So
Eh?
when they give the cross-sectional area, we don't need to square it.
Oh, no need to square it. Right? Question area, they make your life easier, actually. Okay, diameter, they're trying to make your life difficult. So you have to convert to area, then you square it. Okay. Can I? Okay, 24. So come on, give a try. 24. I erase everything. Okay, I'm receiving answers. This is so the answer given is B again. Your friend giving B. Is it B? This graph is a little weird because it never start from origin. Of course, why it never start from origin? Because they took the total length. They never took extension. Normally we plot force versus extension. This one is force versus total length. That means the original length is included. That's why I start from the here, from here. The L naught is the total length. So yeah. So you extend it. Energy is stored. Which area of the graph represents the work done on the spring during the reduction in length? Oh, from T1 it dropped to T2. What is the energy recovered? So of course this is the energy recovered. You get this energy back. You get this energy back. Because you go down, right? Go down, this is the energy recovered. Okay. Okay, represent the work done by the spring. So this is the energy recovered. The work is done by the spring, not on the spring. Work done is by the spring. If the spring does work, the spring going to lose potential energy or gain potential energy? It's going to lose potential energy. You're going to lose potential. If spring does work means you're going to lose its potential energy. Okay. If you do work on the spring means the spring will gain potential energy. When that happen? When you extend it. Okay. When you let it go, it's work done by the spring. Okay, good. So the answer definitely is B. It's B. Mn QP. Okay. So that's about this topic. We're going to do the pasya. So let's see some pasya questions. Okay. So warm up first. I don't think so. I want to go this. Okay, the question now we go for a challenging one straight away. So this is going to be challenging one. The question is this one. Question 24. Yes. You can get the answer for this means you are quite good. Give me the answer. 24. What page is this? This page, page 2. Page 2, 24. Okay, 1 minute for you. Okay, this question might be easier if you plot graph, force versus extension. You can get some idea. That's my advice to you. Force versus extension graph might help you a little. Okay, so I'm receiving answers. Okay, one of you said it's B. Okay, so then I need more answers. One of your friends said it's B. WP is half WQ. The others, please give a try. Give me the answer. Do you get B? Or do you get different answer? Sorry. Okay. Oh, okay. I got another answer C. Another friend saying is C. Oh, it's a mixture now, eh? Oh, equally distributed like this time. Half of you said B, half of you said C. B or C? Okay, let's see it's a B or C. This is interesting. Like a 50-50 share. Okay, B or C. So I think in this case, we plot graph. We plot graph. Okay, we plot graph. So I think if you draw the F versus X graph, I think quite helpful. F versus X. The P and Q are based on law. They have a spring 2K. P is 2K, Q is K. The spring are stretched separately by a force that is gradually increased from 0 up to a certain maximum value. The same for each spring. What is same? Force that is gradually increased from 0 up to a certain maximum value. The same for all. The force is same. Both of them have the same force. So P goes like this. Let's say the force applied, let's say F. Okay. Force applied is F. Okay. Q also the force is applied F. Because Q has a less spring constant. This is the graph of P lah. This is the graph of P, which has a spring constant 2K. The graph going to be less gradient or more gradient? The Q must be less gradient, right? Because small k what? So Q graph going to be less gradient. It's going to be less gradient. So it's going to be like this. But both of them was stretched with the same force. So this is your Q. And it's a Q. Yes. So let's say, yeah. Let's say for the Q, let's say extension is X. For the P, extension should be how many X? Because F over X is, we take it as K. The spring constant is K. F over how many X? The spring constant will be 2K. So it should be X over 2, right? X over 2. Okay, so this is the graph. P has a spring constant of 2K. Q has a spring constant of K. So because spring constant of Q is K without any extra numbers, we say the extension of Q is X without putting any numbers. And P we alter. F should be X over 2. Okay, so in this case, what is work done by the Q? What is work done by the Q? The area under the graph. Okay, the area under the graph of Q is what? Half F X. Okay. What is work done by the P? P is half F. How many X? X over 2. XO2. Yes. So how these two related? Which has more energy? Q more energy or P more energy? Q has more energy, because half Fx is half Fx over 2. So definitely energy of Q is greater than energy of P. That means energy of Q is actually 2 times of the energy of P, right? Correct? Because you see here this equation, energy of Q should be 2 times. This times 2, this times 2, then only going to be same as Q. So here all the equation is in terms of P as a subject. So what is P? So energy of P will be half of Q. Half of Q. So answer is B. So those who got B, good. Any questions? Do you understand the working? So I think the F versus X graph can help you to give the answer. P is 2K, the gradient. Q is K. So because Q, K without number, the extension we take it as X. Both have the same force, same pulling force. So if Q extend for X means P must extend X over 2 because it's more stiff spring. Extension will be smaller. So because area and the graph is the work done, so half Fx, Q is half Fx, half F times X. P will be half times F times X over 2, half of the extension. So here looks like for the same force, the less stiff spring did more work. The Q does more work. Less stiff spring did more work for the same force. So WQ is 2WP. I hope the explanation is quite clear. Do you got idea? So those who got a B is the answer. Okay, so C is wrong. WP equals to WQ. To be in simple format, the less stiff spring will do more work. The more stiff spring will do less work if the force applied is the same. Because more stiff won't extend that much. Okay, so conclusion is B is the answer. Any questions from here? No questions, I hope everyone is understand. Okay, let's go to the another challenging one. Okay, now it's going to be all challenging one. Okay, next. The question I'm going to show you is the question faced difficult by your seniors. Okay, this one. 22. Okay, class, come on. You already did many questions. Hope everyone give me the correct answer. 1 minute for you. 22. This is what page is this? Sorry, it's page 11. Page 11, question 22. You are working? Give me the answer. This time both extended to the same extension. Asking what is the ratio of the tension of P and Q. Draw the two wires diagram, put the quantities in a correct ratio. AO2, LLO2, force, they never mention what is the, they want the ratio of tension. Ratio of tension is actually ratio of the force, right? The tension here is the force, right? Okay, so I receive answer D. One of you said this D. I receive only one answer. Come on, the others. Okay, two of you say D. Okay. Two of you say, okay. So one of you said B, boy. So I got answer D and B. Two of you said D. One of you said B, boy. So I need more answers. Come on. B or D? Getting more answers for D. So looks like D, is it? Oh, okay, many giving me D. I think majority giving me D. Okay, let's see. Is it D? Okay, so yeah, as usual. So what do you do? So the first wire P, and wire Q. Wire P as a L of wire P as a length of L. As a length of L. And cross sectional area is A. Oh, A. And wire Q is length is 2L. 2L. And the area is how much? Area is AO2. Area is AO2. Then they're asking, what is the tension P? The force law, the tension P, tension Q. Tension Q. Extension was the same. Both has the same extension. This X, this also X. We take it as X, both X. Okay. So as usual, Young modulus is same. So Young modulus same. So the first wire P, force is TP. L is L. Okay, we put L. Over area is A. Extension is X. Should be equals to TQ. L is how much? 2L. Area is how much? Area is AO2. This is just substituting. This is the formula. So just TP over TQ. TP over TQ, what do you get? TP over TQ, you get 4. You get exactly 4. It's maths. You see 2 here is half. So half 2 divided by half, you get 4. You get 4. So it's actually 4 1. So good. So it's clear. Answer is D. Okay, those who got D, very good. So those who didn't get, please check this how the calculation. I think you might make a small mistake here. Okay, so this is how they input the information. Any questions? Okay, I'm happy that many of you trying. Those who have never tried, please come forward, give me your answers, try to participate. That's for your own good. Okay, you'll be learning. Okay, if you never participate, then your learning process will be not that good. Okay. Okay, we proceed. More questions? Let me show you. Okay, this one. Okay, question 20. What's answer? This is November 5, I think page 14. Let me expand a little. Okay. Getting the answer quite fast. Good. Okay, so getting B again. B. Is it B? Or many of you saying B? Which area represents the network done on the sample? Yes, network done. Okay, I never use the term network done. The network done is the energy stored minus the energy recovered is the network done. Okay, energy stored minus the energy recovered. So energy stored is X, Y, Z. Energy recovered, of course, is Z. So energy stored minus energy recovered is the network done. So X plus Y, no doubt about that. So answer is B. In this case, all of you giving me B. Good. So B is answer. So another name for the energy trapped is network done. Network done means energy stored minus energy recovered is the network done. Okay. Okay, this is tricky one. 22. It's quite tricky. Be careful. Question page 15, question 22. Oh, sorry. Let me pull this up. Okay, question 22. Be careful, it's tricky. 1 minute for you. What is the total work done in searching the sample from 0 extension to 12 mm? The trap is simplify the calculation by treating the region XY as a straight line. That's the trap. So anyone got the answer? No answer so far. So they ask you to treat XY as a straight line. Okay. So I'm receiving the answer. B. If your friend says B. Is it B? 3.55 joules. See, the trap is the. So I get more answers. Oh, now another one said is a D. 6.6 joules. 3.55 or 6.6 joule. Okay, the trap is this. The trap is they ask you to treat this as a straight line, XY as a straight line. But don't take OX and XY is a same gradient. OX and XY different gradient.
Oh.
That means the first one is what area? It's the area of a triangle. The second one is what shape? Second one, the area is what shape? It's trapezium. It's a trapezium. So the area of 1 plus the area of 2 should be the total energy. Area of 1 is what? Half times how much? 50. The pause is 50 times extension how much? 10 mm. So 0.01 half fx plus with A2. A2 is a trapezium. The shape is like this one. Shape is like this. So what is the trapezium formula? Half A plus B H, right? Your trapezium. The side is A and B. H is the separation, right? H. So in this case, half times A is what? A is the height, 500 and 550. So 500 plus 550 times what? Times with H is the separation, 2 mm. So 0.002 meter. Yeah. Yeah, half times APH. Yes, this gives you the answer. 2. What's the answer? You get 6.6 or 3.5? 25 times 0.25. 0.25. 500,000. So B, So 3.55.
Sir,
Yeah.
if we treat the xy as a straight line, shouldn't the shouldn't the y be higher a bit?
Y is higher. Yeah. Y is higher. Yeah. Correct.
Shouldn't it be higher than 550? Because if we want to treat it like a straight line, or should we just ignore it?
No. The curve is treated like a straight line. Right?
Oh, okay.
The curve is treated like it. So the maximum point is still 550.
Okay.
So those who got 355 and those treated as trapezium, then you are in a correct track. I think out of 100%, I think about 95% of students never really look into this. Okay, they treat everything as a triangle and get the answer. So that make a mistake. Previous experience lah. So that's a trap here. Okay. Okay, good. So let's proceed. More questions? We do another 2, then we stop. Okay, only 2. Another 2, Okay. Another 2 questions. Okay. Question 19, what is the answer? Question page 20, question 19. What is plastic deformation? So this is what is meant by plastic deformation? Yes, B, Yeah. Yes, all of you giving BP. Good. So plastic deformation occurs, the B answer. When the load is removed, the material contracts, but permanent stretching happens. A, answer A, plastic deformation occurs, strain is not proportional to stress. But when the load is removed, the material returns to, no, it's wrong. It's never returns to original length for plastic deformation. C, plastic deformation occurs until the extension is no longer proportional to the load. No. When the load no longer proportional to the extension, it could be elastic also. What? From limit of proportional to elastic limit, the extension no longer proportional to the load. What? But so that it could be elastic deformation. So C is not necessary. D, plastic deformation occurs when the material extends to a strain directly proportional to the stress. Strain directly proportional to the stress is still elastic deformation, no plastic deformation. So yeah, B is the answer. Okay, so last question for today. Last question, okay. 23. Page, what page is this? Page 28, question 23. Okay, last question for today. Hope everyone give me the same answer. Oh, this is straightforward. What's the answer? Okay, so yeah, this is straightforward. The answer is C, half fx. The area under graph is your energy stored. Yeah, many of you say, all of you say C. Okay, half fx. Okay, half fx. Okay, so good. Okay, class. So you have many questions in this paper. A lot of questions. Okay, as the background, your semester exam just about 3 weeks away. Okay, 3 weeks away. So at the background, please do all these past years. Get ready. Okay, so we going to start with a new topic tomorrow. Waves. I'll leave this topic to you. At the background, just do more questions. Okay, so tomorrow we're going to start with a new topic, wave. Okay, wave is considered as one of the toughest topic in AS. Okay, tricky. Wave got 2 topics. The one we're going to do tomorrow is not that challenging. The following one is challenging, related to wave. 2 wave topics, wave and superposition. Okay, but to understand the superposition, you must understand the wave quite well. Okay, so get some idea about wave. So I see you tomorrow. Okay, so tomorrow we're going to start with a new topic. So deformation solid, do more questions, be prepared. Okay, I might give you a tutorial later maybe for the remaining topics we haven't done yet, but not this, maybe next week. Okay, so any questions so far? No questions, Okay, so keep it up, do more questions. A levels will be for you if you consistent with your doing questions. Okay, the more passes you do, you'll be more prepared. Okay, for physics. Okay, so if you don't have questions, I see you tomorrow. Any questions?
No.
No questions, Okay then. See you tomorrow, tomorrow 10 o'clock. Thank you.